quadratic equations by finding square roots. And essentially in this lesson, we are just learning about working with square roots, operating with square roots, and everything like that. Okay, so on the top here, we have a couple of vocab related items. So we have the square root. So anything under the square root we call, or a radical, which would be this symbol right here. Anything underneath that we call the radicand. Okay? So for our radicals, we have positive radicals, which would have a positive coefficient. So a number right out here in front would be positive. We call that a positive radical. And then we also have negative radicals. Okay? And in some cases, we'll have a plus minus or a positive negative. So that would be both. Okay. So with our radicals, we can use the product property. So if we take the square root of a times the square root of b, that equals the square root of a times b, right? We can also substitute real numbers in for our variables. So that would be like the square root of 2 times the square root of 3 equals the square root of 2 times 3, which is just 6. Okay, very similarly with division, if we have the radical of a divided by b, or that fraction a over b, we can split both our a and b's into, both of our variables, into separate radicals. So for example, if I had the square root of 1/4, 1 over 4, that equals the square root of 1 over the square root of 4. Okay? From here, in this example, I can simplify both of these. The square root of 1 is just 1, and the square root of 4 is just 2. So that gives me 1/2. Okay? A radical expression is in its simplest form when no radicand has a perfect square factor other than 1, the radicand contains no fractions, and no radicals appear in the denominator of a fraction. This is the whole no tenths in the basement analogy there. Okay? So an example of rule 1. No radicand has a perfect square factor other than 1. So if we were to factor all of these radicands, so the term underneath the radicals, we need to check to make sure that no perfect square can factor from any of those numbers. In our first example here, we have the square root of 8. Okay, if you start thinking about your factors of 8, you have 1, 8, 2, 4, and that would be it. But 4 is a perfect square, so we must factor 8 into 2 times 4, or 4 times 2. Okay, 4 is a perfect square, so we must simplify that. Okay, we could first split this up to be the square root of 4 times the square root of 2. We can simplify the square root of 4 to give us 2 times the square root of 2. Okay, so that would be the simplest form for the square root of 8. You can use a very similar process with negatives. So like in number 2, we have a negative out in front. So we could rewrite this right away as negative 1 times the square root of 49. Okay, that is an equivalent statement. So 49 is a perfect square, so we must simplify it. So the square root of 49 is just 7. So you have negative 1 times 7, which just gives you an answer of negative 7. Okay, give these next two a try on your own, and we'll look at those during class. All right, the next section here is multiplying like roots. So you can multiply your coefficients, you can multiply your radicands. So do that and then simplify it. Okay, so let's start by multiplying our coefficients. So in this case, we can multiply our -2 out in front and our 3. And then in our next step, we can multiply our radicands. So 10 and 40. So -2 times 3, that gives me -6, times the square root of 10 times 40, which is just 400. From here, we can go ahead and simplify. I've got -6 times the square root of 400, which is just 20. Okay? And then I've got -6 times 20, which gives me -120. Okay, so when you have like roots, pretty straightforward. Okay? Roots refers to the degree of your radical. In this case, we're just working with square roots. The same rules would apply for cube roots, and so on and so forth from there. Okay? In order to add or subtract, we need to have like radicals. So simplify individual terms and then add the coefficients. So in this case, in number 7, we cannot simplify this right away because we have the square root of 27, the square root of 3, and the square root of 12. They are not like radicals, so we cannot simplify them right away. Yet, we could simplify the individual terms so that they all share the same radical. Okay, so let's go ahead and start simplifying each of these individually. Okay, if I'm looking at each of my radicals at 27, 3, and 12, this one's fairly easy to see, but we have a common factor of 3 between each of these terms. So let's simplify it that way. Okay, so I have my 3 as my coefficient. In order to get a square root of 3, we could simplify 27 as 9 times 3 minus 7 times the square root of 3, which we cannot simplify, minus the square root, and we can simplify 12 as 4 times 3. Okay, so let's go ahead and simplify each of our terms individually. So I have the square root of 9, which just gives me 3. So I have 3 times the square root of 3, minus 7 times the square root of 3. Nothing changes there. And then I'll take the square root of 4 here. So that's minus the square root of 4, which is just 2 square roots of 3. Okay, I better go ahead and simplify my coefficient here. So I've got 3 times 3, which just gives me 9 square roots of 3, minus 7 square roots of 3, minus 2 square roots of 3. Okay, now at this point, I have like radicals, so I'm good to add or subtract. In this case, we are subtracting. So what we need to do is we need to subtract our coefficients, and then our radicals will actually just stay the same. So I have 9 minus 7, which is 2, minus 2, which is 0. So ultimately, this gives me 0 square roots of 3. 0 times anything is just 0, so my final answer in this case is just 0. Okay? The key takeaway here is you need to have the same radicals in order to add or subtract. Okay? Try 8 on your own, and we will take a look at that one during class. Another huge aspect of our radicals is that you can use the distributive property. You can multiply radicals. Okay, so in example number 9 here, let's use the distributive property to distribute 2 square roots of 3 to each of our terms here. So if I was to multiply 2, remember, multiply your like roots. You would multiply our coefficients. So we have 2 times 3, which is just 6. Square root of 3 times the square root of 6. So just 3 times 6 gives me 18. Plus, go ahead and multiply our coefficients. We have 2 times 4, which just gives me 8. Square root of 3 times square root of 8, which is the square root of 24. Okay, at this point, In order to simplify, I'm going to have to simplify each of my radicals by factoring out our perfect squares. So I've got 18. 9 is a factor of 18, so I'll just make that 9 times 2 plus 8 times a perfect square that can factor from 24 would be 4. So I've got 4 times 6. Go ahead and simplify both my radicals. The square root of 9 is 3. So we've got 6 times 3 square root of 2. And in this case, I have the square root of 4, which is just 2, plus 8 times 2 square root of 6. Okay, might as well go ahead and simplify my coefficients here. I've got 6 times 3, which is just 18. Square root of 2, plus 8 times 2, which is 16. Square root of 6. Okay? At this point, we can look to simplify, yet there is no way for us to get like radicals between 2 and 6. So we have to leave it in that form. We cannot add those two together. Okay? They are not like radicals. All right, so for number 10, try that one on your own as well. This is one we will for surely look at during class. The key to number 10 here is that you will have to FOIL. Okay, so your distributive property in this case is FOILing your two sets of parentheses. Okay. All right, moving on to page number 2. So examples of rule number 2. The radicand contains no fractions. Okay, we don't want to have any fractions, especially in the denominator. Okay, so taking a look at 11 here. Remember, when you have a fraction like this, you can split your radical into two different parts. So this is the same as having square root of 5 over the square root of 4. At this point, all we need to do is simplify. We cannot simplify the square root of 5. So we've got the square root of 5 over the square root of 4, which is just 2. So this fraction simplifies to the square root of 5 over 2. We do not want the radicand to contain fractions, okay? And especially not the denominator. Okay, try number 12 on your own. This one simplifies very nicely. All right, rule number 3. No radicals appear in the denominator of a fraction. Okay, I kind of already referred to that in rule number 2 here. So let's multiply the numerator and denominator by the denominator's conjugate to get rid of the radical. All right, so the conjugate is when you essentially multiply something by the denominator to undo the radical. Okay, so if we just have the square root of b, its conjugate is the square root of b. Multiplying those square roots by each other undoes the radical. Okay, it will leave you with the result of b. Okay, if you have a plus the square root of b, its conjugate is a minus the square root of b. Vice versa goes with a minus the square root of b. Its conjugate is a plus the square root of b. Okay, so use those conjugate rules in order to rationalize the denominator or undo the radical. Okay, let's look at a couple of quick examples here. So for number 13, if we want to get rid of our radical in the denominator, let's multiply it by the conjugate. The square root of 2, its conjugate is just the square root of 2. It's our top rule right there. So we have to multiply it by the square root of 2. And if we're to multiply our denominator by the square root of 2, we must also multiply our numerator. So square root of 2 times square root of 2, that would simplify to give you the square root of 4 over 5 times the square root of 2. Okay, we can't simplify our numerator, but we can simplify our denominator. And this gives us 5 square roots of 2 over 2. Okay, you can notice in your final answer, you do not have any radicals in the denominator. Okay, for example 15 here, we need to multiply by our conjugate of just our denominator. Okay, so look at just your denominator. Okay, for the conjugate, all we have to do is flip our sign in our two terms. So we must multiply by their square root of 3 plus 5. And if we do that to the denominator, we must also multiply it by the numerator. Okay, if we were to multiply this, you would have to FOIL. Okay, so if it helps, feel free to put parentheses around your sets of terms. So we have square root of 3 times square root of 3, which gives me 3. Square root of 3 times 5. We can just make 5 square roots of 3. 2 times the square root of 3, which gives me 2 square roots of 3. 2 times 5, which gives me 10. All over square root of 3 times square root of 3, which is just 3. Square root of 3 times 5, which is 5 square roots of 3. Negative 5 times square roots of 3 gives me negative 5 square roots of 3. Negative 5 times positive 5 gives me negative 25. Okay, something before we go and simplify this complex looking fraction that I notice is that we have 5 square roots of 3 minus 5 square roots of 3. And obviously, those two are just going to cancel. So that helps us simplify this fraction a lot. Okay, we may need to write in the margins a little bit here. So let's go ahead and simplify. Let's add our like terms. So 3 plus 10 just gives me 13. 5 square roots of 3 plus 2 square roots of 3 gives me 7 square roots of 3. All over 3 minus 25, which just gives me negative 22. Okay, at this point, it is really okay to leave this just like this, but for formality, usually we don't keep a negative in the denominator, so we could just flip that negative into the numerator, and these are very equivalent statements. So it gives me negative 13 minus 7 square root of 3, all over positive 22. In reality, I'd be really okay with either of those two solutions, okay? As long as you do not have a radical in the denominator. Okay? So we're going to leave 14 and 16 for you guys to do on your own. Most likely we'll look at them during class, especially number 16. All right, final example here. Remember that the solutions to the following are roots, okay? Remember when we first talked about roots, the square root symbol to the equation, remember there will always be two roots, okay? This is the key to solving any problem where you have to take the square root when you have an x squared or something like that. Okay, so let's take a look at number 17. So in order to solve for x, we need to isolate our variable like always. So let's go ahead and subtract 5 from both sides. That leaves me with 3x squared equals 41 minus 5, which is just 36. Okay, go ahead and divide our coefficient. Divide both sides by 3. That leaves me with x squared equals 12. Okay, if we want to solve for x, we have to take the square root of both sides in order to undo our square. That leaves me with x equals plus or minus square root of 12. This is our two roots part. You will get a plus and a minus. Okay, we can't leave this just like this because 4, which is a perfect square, is a factor of 12. So we can simplify this as x equals plus or minus the square root of 4 times 3, which ultimately simplifies to plus or minus 2 square roots of 3. Okay, and that is our solution. We will have 2 answers to these questions. Okay. In order to keep the video somewhat reasonable in length, we will also skip 18. Make sure you're trying these on your own, working with radicals and square roots in this case. It may seem a little difficult at the start, yet with a little bit of practice, you'll realize that it's really not all that different than working with typical equations that we have been looking at in class. Okay, so give those a try on your own. We will take a look at them during class. Make sure you bring questions. Thanks for watching.